Using the idea of the previous example, when many forces act at a point or a particle or a point mass, the sum of all the forces is equal to net force. This is the reference point. R is the position vector of this point mass with respect to the reference point, about which you are going to calculate the torque. So, the line along which the net force acts is called line of action. The line along which the particle moves may not be collinear with the line of action. It may experience the force in this direction. However, it may move in some other direction. Let us assume that this is the line of motion. At this point, this is the line of motion because this is the velocity vector. We know that the torque the net torque experienced by the point mass about O is given as tau O is equal to R cross F net. Since this is net force, Newton's second law states that whenever a net force acts on a particle, the particle's momentum, the linear momentum will change. The net force acting on the particle can change the linear momentum. Therefore, you can write F net is equal to time derivative of the linear momentum of this particle. And this stuff is multiplied with this position as a cross product. This can be written as d by dt of R cross mv, because d by dt of A cross B, the time derivative of A cross B can be written as derivative of A vector cross B vector plus A vector cross derivative of B vector. This is a vector operation. Here A is R, A vector is R vector, B vector is MV vector. d by dt of R cross MV can be written as d by dt of R vector cross MV plus R vector cross d by dt of MV vector. Since the rate of change of position vector is the velocity vector, the first term can be written as V cross MV and the second term will remain as it is. The first term can be written, since M is a scalar, you can pull it out of the cross product. So M into V cross V plus R cross d by dt, a time derivative of the momentum, linear momentum of the particle. We know that any vector, when it is cross multiplied with that vector, or an equal vector? It will be 0 because V cross V is equal to V into V mod of V into mod of V into the sine of the angle between these two equal vectors. Angle between two equal vectors is 0 degree, therefore that this term will vanish and we are left behind with this term. So R cross the time derivative of mv is equal to the time derivative of r cross mv. Therefore, I wrote r cross d by dt of mv is equal to d by dt of r cross mv. After you understood this point, then we will be fit for further discussion. The discussion is that in the particle mechanics, force changes something. That something is the linear momentum, where linear momentum of the particle is equal to mass times velocity. This is the linear momentum of the particle. When the force changes linear momentum, we should expect that the rotational analog of the force, should change something. And actually it is changing something. But this something is a strange looking term, r cross mv. Tau is equal to d upon dt of r cross mv. mv can be written as p vector, linear momentum vector. So tau, the torque, must change something. We expected that the torque will change something, and really it is changing something, and that something is called angular momentum. It is named angular momentum because force changes the linear momentum. The angular analog of the force, that is torque, should change something. That something should be the momentum. Since it is the torque is the angular analog of the force, this particular term should be the angular analog of the linear momentum, that is angular momentum. The angular momentum changes when a torque or a net torque acts about a point. So torque about the point O can be written as d by dt of angular momentum. We name it like that. This angular momentum can be written as L vector, where r cross phi is defined as the angular momentum L vector. This angular momentum of the particle is measured with respect to the same reference point. So whenever there is a net torque acting on the particle, or whenever a particle experiences a net torque about a certain point, about that particular point, that particle must change its angular momentum, and the torque, the net torque, will be numerically equal to the rate of change of angular momentum of the particle about that same reference point. The net torque about O is equal to the rate of change of angular momentum of the particle about O. The net torque experienced by a particle about O is numerically equal to the rate of change of angular momentum of the particle about the same reference point O. This is the Newton's second law for turning of a particle. Let me analyze the physical significance of angular momentum. Angular momentum changes only when the particle will experience a net torque. And the net torque experienced by the particle is equal to rate of change of angular momentum. The net force acting on the particle is equal to the rate of change of linear momentum. This is the Newton's second law for translation. This is Newton's second law for turning. This is Newton's second law for translation. So, in this chapter we are discussing the concept of torque and angular momentum experienced by a particle or acting on a particle. The angular momentum of a particle of mass m velocity v with respect to a point O. The velocity is v, mass Vm, the position vector of the particle with respect to the reference point, let it be r. The angular momentum of a particle of mass m, velocity v, and position vector r with respect to this point is given as L is equal to r cross mv. We define this term as angular momentum because this is a linear momentum which is changed by the net force, and this entire quantity is changed by the net torque. Torque is the angular analog of the force. Therefore, this quantity should be named as the angular analog of the linear momentum. Therefore, it can be called angular momentum. Since it is multiplied with the distance, this can also be known as moment of momentum. Angular momentum can be called moment of momentum because momentum is multiplied with a distance, and this multiplication is not ordinary multiplication. This is a cross multiplication or vector multiplication. This linear momentum can be written as P. So, the angular momentum of a point mass about a given reference point is equal to position vector of that point mass with respect to the same reference point O cross the momentum of that point mass with respect to the same reference point. For the sake of simplicity, let this reference point be stationary. So the velocity V is the velocity of this point with respect to ground. R cross P can be written as Rp into sine theta. When this is the velocity, in the same direction the linear momentum will point, because P is equal to m into V. Since m is a scalar quantity, velocity vector and linear momentum vector must be collinear, unidirectional. It must be unidirectional. Well, bring the tails of these two vectors, vector r and vector p, to same point, and the angle between these two vector is theta. When it is p sine theta, that is perpendicular to the r vector. This is a component, the perpendicular component of the linear momentum onto the r vector, and there is a parallel component also, that is called p parallel. P sin theta can be written as p perpendicular. This can also be written as r sin theta into p. In another way, we can write this is r vector, this is linear momentum vector, r sin theta. Instead of taking the component of the linear momentum, here you should take the component of the r vector perpendicular to the momentum vector, that is r sin theta. So r sin theta is the perpendicular distance dropped from the reference point onto the line of motion. This is the velocity vector, or this is the line of motion. This is r sin theta, or we can call it perpendicular distance. Small p, that is capital P, represents the linear momentum. Small p represents the perpendicular distance. R sin theta can be written as small p into capital P. In this way also, you can represent the angular momentum vector, its magnitude about any reference point, r into perpendicular component of the linear momentum to the position vector is equal to the perpendicular component of the position vector onto the, with respect to the linear momentum vector into the magnitude of the linear momentum, r p perpendicular or p or r perpendicular into p. So with this theory, let us do some problems. Let the particle of mass m moves with constant velocity about any reference point. Prove that the angular momentum of the particle is a constant quantity about any reference point. You take this reference point O, this is the position vector of the particle, the angular momentum about this point O is equal to r cross mv. This can also be written as RMV sin theta, and angle is given by A cross B idea. This is A, this is B, A cross B, R cross MV, R cross MV. So the angle gives a sense of clockwise direction. The angle moves in a clockwise sense. Therefore, the angular momentum of the point mass with respect to this reference point is clockwise. Now, you take r sin theta. The r sin theta is nothing but the perpendicular distance. So, you can just write small p into mv. And the direction is clockwise or inward or minus k cap direction. This is a fixed quantity. Direction is fixed. Since it is moving with constant velocity, the perpendicular distance is also a constant quantity, and mass is a constant quantity. Therefore, the magnitude also is a constant quantity, and direction also is a constant quantity. Therefore, the angular momentum vector is a constant vector. The angular momentum of the particle is a constant. L vector is constant. When a particle moves with constant velocity about any point, reference point, inertial reference point, that point may move with constant velocity or that point may be stationary. About any reference point, inertial reference point, the angular momentum of the particle is a constant vector or constant quantity. You can use it as a theorem also. Well, let us take another example. Find the angular momentum of the projectile. When you throw the stone, it will move in a parabolic path. At this point you are throwing, it's called point of projection with velocity v naught and angle theta naught. With respect to horizontal, the horizontal is x-axis, the vertical is y-axis. At any point you can take the topmost point. Find angular momentum at the highest point. With respect to the origin. So at the highest point, this particle moves with a velocity v is equal to v naught cos theta naught, because its horizontal component of the velocity or the linear momentum will remain constant because the net force is acting down, that is gravity force. Assuming no air resistance, no air flow, no other force along x direction, its momentum can be conserved along x direction, conservation of linear momentum. Using that principle, the linear velocity of the particle along x direction, along horizontal direction remains constant. Now, position vector of the highest point with respect to the point of projection or the reference point O. Let us assume that this distance is x and this distance is y. So its coordinates can be written as x, y, x comma y. So r vector can be written as x I cap plus y j cap. mv vector can be written as mv naught cos theta naught I cap. Now r cross mv is the angular momentum of that point mass with respect to the point of projection. X I cap plus y j cap, that is r cross, r cap cross mv naught cos theta naught I cap. I cap cross I cap is 0. And we are left behind with the second term, that is mv naught y j cap cross I cap, I cap j cap k cap, I cap cross j cap is equal to k cap. But we have j cap cross I cap, j cap cross I cap is equal to minus k cap. Minus mv naught y k cap. This is the magnitude and minus k cap is the direction, or you can write mv naught y in clockwise direction or inward direction. Here we need to calculate the value of y, and we have to write the cos theta factor also. Y is equal to the maximum height, and that is equal to v naught square sin square theta by 2z. In projectile motion, you know this formula. When you substitute this, m v naught cos theta naught into y as v naught square sin square theta upon 2g into minus k cap. This gives us m v naught cube sin square theta by 2j into minus k cap. Answer. This is the angular momentum of the particle about the point of projection. You can use this idea or directly also you can do it. As an alternate method, you can write L is equal to r cross mv. R and mv, bring these two vectors to a point. This is the velocity, this is the velocity. R and mv, between these two vector, let us write the angle theta. R cross mv, R cross mv. So the angle is moving in clockwise sense. So you can just write r mv sin theta in clockwise sense. And r sin theta is nothing but the maximum height. R sin theta can be written as maximum height y max or h max into mv. V is written as v naught cos theta, and y max you can calculate from this. You can y max or h max you can calculate. And already you have calculated, you can just substitute and to get the same answer. So slight change of the first step, you can get the same answer. A clockwise direction means minus k cap direction or inward direction. Well, from this example we understand that this angular momentum of the particle, it depends upon the reference point. If you choose this point, you can find its angular momentum about this point, that will be different. When the particle was here, its angular momentum with respect to the same point will be 0. So angular momentum keeps on changing. And we will prove in the next section that the rate at which this angular momentum is changing is none other than the torque acting on the particle by gravity about this point.